Hello everyone, this is Dr. Shivam Mishra and I am here with the new session of refrigeration and air conditioning for discussion discussing a topic refrigerants and their properties. Firstly, I will go with the general description of refrigerant, what are the different kind of refrigerant, then it will be proceeded with the different properties and then the what are the different nomenclature of refrigerants. So initially with the general description I will start. The efficiency of any refrigeration system mainly depends on its operating condition, that is mainly the temperatures. One is your evaporator temperature or the source temperature where the absorption of energy takes place and the change of phase of a refrigerant takes place and the refrigeration effect is produced. Another is your higher temperature or the sink temperature or the condensing temperature where the heat rejection takes place. However, important practical issues such as system design, size, initial and operating costs, safety, reliability depends on the type of refrigerant selected for a given application. It means we cannot select any refrigerant for any particular application. There should be some proper guideline for the selection of refrigerant, otherwise it will change its system design, size, initial operating costs, safety, reliability, etc. So due to the depletion of ozone layer and global warming, one more point is here, due to the depletion of ozone layer and global warming, the selection of suitable refrigerant has become one of the major issue. These are two main problems which world is facing, the world is going through, and it is become hazardous day by day. So the selection of any suitable refrigerant is very important. Another point is, if any existing refrigerant is replaced, if there is any existing refrigerant and we are going to replace it, it may cause several changes such as the design, the manufacturing of any refrigeration system. So we cannot go randomly for any refrigerant for any particular use. There should be some proper guideline for the selection of the refrigerant for a given application. Now, moving towards the different kinds of refrigerant, the refrigerant suitable for refrigeration purpose can mainly be classified into two parts, namely primary and secondary refrigerant. Primary refrigerants are the refrigerants which are used directly as working fluid. For an example, in vapor compression and vapor absorption refrigeration system. For an example, in vapor compression refrigeration system, we have used R11, R12, NH3, carbon dioxide as the primary refrigerant, and these refrigerant undergoes a phase change in evaporation process, condensation process or the absorption process. For an example, if I will draw a pH curve, pressure enthalpy curve, so this the point 1, 2, 3 and 4. Point 4 to 1 is your within the evaporator. So this produces your refrigeration effect because here the absorption of heat takes place from the confined space, and here your refrigerant changes its phase and which is represented by latent heat of vaporization. When the liquid refrigerant comes in the evaporator, it uses this energy and changes its phase to the vapor phase. So primary refrigerant generally go with the change in phase. Secondary refrigerants are the refrigerants which are used for transporting thermal energy from one location to another location. These cannot be directly used as a refrigerant. They are firstly cooled by the primary refrigerant, then they are used as a refrigerant. These are also known as the brines or anti-freezers. Next point is, if the operating temperatures are above 0 degree centigrade, then pure water can also be used as secondary refrigerant. For an example, in large air conditioning system, water is also used as secondary refrigerant. Unlike primary refrigerant, secondary refrigerants does not undergo any phase change as they transport energy from one location to another location. It means what is the basic difference between a primary refrigerant and the secondary refrigerant? That is, the primary refrigerant undergoes a phase change during the evaporation, condensation or the your Absorption process, while a secondary refrigerant does not undergo any kind of phase change while it transport energy from one place to another place. One more point to be noted is that temperature or the freezing point of the brine or the secondary refrigerant is always lesser in comparison to the freezing point of its constituent elements. So what are the different refrigerant selection criteria? The refrigerants are generally selected on the behalf of their few properties that are mainly thermodynamic and thermophysical properties. Another is your environmental and safety properties, and third one is your economical point of view. So we cannot directly select any refrigerant for any particular application unless until we evaluate their thermodynamic and thermophysical properties, environmental and safety concern, and the economical issues. So firstly we will discuss about the thermodynamic properties. In this, the first point is the boiling temperature. The boiling temperature of refrigerant at atmospheric pressure should be low. So this is the point to be noted, that the boiling temperature of a refrigerant at atmospheric pressure should be low. If the boiling point of a refrigerant is very high at atmospheric pressure, so what happens? The compressor should be operated at high vacuum. This is the point to be noted. If boiling point of a refrigerant is very high at atmospheric pressure, then compressor should be operated at high vacuum. Second point is freezing point. The freezing point of the refrigerant should be well below the operating temperature of the evaporator. The freezing point of a refrigerant should be well below the operating temperature of the evaporator. So here are some freezing points of different refrigerants. R22 has a freezing temperature of minus 160.5, R12 has minus 157.4, NH3 or ammonia has minus 77 degrees centigrade, R134 has a freezing point temperature of 101.2 degrees centigrade. One more point which is very important, that freezing point of water is 0 degrees centigrade, and below this temperature water is converted to ice and hence the flow is not possible. So water is not used as a refrigerant. This is the reason, because if the operating temperature is well below the 0 degree centigrade, the water converts its phase and becomes a solid, and it cannot flow. Another thermodynamic property is your critical temperature. Critical temperature of a refrigerant should be as high as possible, or at least above the condensing pressure and temperature. The critical temperature of a refrigerant should be as high as possible, or at least above the condensing pressure and temperature, because we can understand this by drawing a curve, that is a pH curve. If I'll draw a pH curve here, this is your pressure, this is your specific enthalpy. So this one is your critical temperature, this is your critical point, and here it is written that critical temperature of the refrigerant should be as high as possible, or at least above the condensing temperature. So let us assume this is your point 1, this is your isentropic compression process, this is your condensation process or condensation pressure, this is your evaporating pressure, this is your PE evaporating pressure, this one is your PC condensing pressure. So if I'll increase the condensing pressure, if I'll increase the condensing pressure, and now if it reaches towards the critical point, we can see on the pH curve that the enthalpy difference, that is H2 minus H1, increases. Again it reaches to 2 dash if I'll increase, and it is reaches to 2 double dash. So H2 double dash minus H1 is always higher in comparison to H2 dash minus H1 is always higher in comparison to H2 minus H1. It means work input to the compressor is always increasing. So if work input to the compressor is increasing and refrigeration effect remains the same, the COP of the cycle may reduced will always be reducing. Refrigeration effect divided by work input to the compressor, and if this increases, COP reduces for the given refrigeration effect produced. Also we can see the critical temperature of a refrigerant is the highest temperature. Listen carefully. It is the highest temperature at which it can be converted to a liquid regardless of its higher pressure. If it is too near to the desired condenser temperature, there is always higher power consumption. As I already told you, that if it is near the critical temperature, there will always be higher work input to the compressor, and again it will result in a higher power consumption. These are the notes. There is one note: the critical temperature for ethylene and carbon dioxide are almost undesirable for Indian summer condition. That is, carbon dioxide has a critical temperature 31 degrees centigrade and ethylene has a temperature of minus 10.2 degrees centigrade. So these two refrigerants are having undesirable critical temperatures. These are the few critical temperatures for different kind of refrigerants. So we'll discuss another property, another thermodynamic property, that is your specific heat. So specific heat for a vapor should be as high as possible in order to limit the degree of superheat. We can understand this by this one. H2 minus H1, the difference of enthalpy at the entry and the exit condition to the compressor. If this increases, it means it can be written as CPdt. Enthalpy difference can be written in terms of temperature as CPdt, and if Cp of a vapor is high, the delta T reduces. This delta T is your degree of superheat. So for a lesser degree of superheat, the higher Cp value is expected for a vapor. Also, specific heat of a liquid refrigerant should be low in order to limit the degree of irreversibility. That is the lower value of change in entropy. Here we can understand by this one that TDS equation can be written as dH minus VdP. If the pressure is constant, this term becomes 0 because change in pressure is 0. Now dH, enthalpy difference, can be directly written in terms of temperature and CPdt. If Cp is to be minimized, if ds is to be minimized, or this is your change in irreversibility, change in entropy. Change in entropy is to be minimized. We know that it is directly proportional to the Cp value. So if change in entropy is to be minimized, there should be a lower Cp value for a liquid refrigerant. Now next property is enthalpy of vaporization. It should be as high as possible because for the same refrigeration capacity the mass flow rate reduces. As I already told you that refrigeration capacity is given as m dot, that is mass flow rate of the refrigerant, multiplied by the refrigeration effect produced. So if for a given refrigeration capacity, if the refrigeration effect or the enthalpy of vaporization, which is written by HFG, is higher value, so we will have a lower mass flow rate of refrigerant, and hence the lesser power consumption will also be resulting. For the commonly used refrigerant, ammonia has the higher value for the enthalpy of vaporization. There are different refrigerants which are used. So ammonia is the refrigerant which has the higher value of enthalpy of vaporization. So here are few enthalpy of vaporization for few of the refrigerants. We can see that H2O has 2261, NH3 has this one. So we generally do not prefer H2O as the refrigerant apart from your few application, because it's if the operating temperature is well below the 0 degree centigrade, it becomes in the solid form and it freezes the pipe and it cannot flow, and hence it will not produce the refrigeration effect. H2O is not preferred. Here it is written. Okay. Next one is your thermal conductivity. It should be as high as possible as it helps in reducing the size of evaporator and condenser. We have already studied it in your heat and mass transfer, where we had discussed about the heat exchanges, and evaporator and the condenser part were discussed. So we know that Q is given by your formula minus Fourier's law minus Ka dt by dx. Here Q, heat transfer, rate of heat transfer is directly proportional to your area. Or now for a given heat transfer rate, we have inverse relationship between the thermal conductivity as well as the area. So for the lower size of the heat exchanger, that is your evaporator or the condenser, the refrigerant must have a higher value of thermal conductivity. Next is evaporator and condenser temperature. Here it is written that both should be positive. If evaporator pressure is less than atmospheric pressure, then there is a possibility for the leakage of air. There will always be a negative pressure. So the refrigerant which is being used, there will always be a leakage of the air. So evaporator pressure should be kept almost equal to atmospheric pressure, where the condenser pressure should be well above the atmospheric pressure or a moderate pressure value. Next point is your compression ratio. Compression ratio is given by P2 by P1, or we can say it is not P2 by P1, it is the condenser pressure ratio to the evaporator pressure ratio. It is your compression ratio. It is defined as the ratio of volume of the refrigerant before compression to the volume after compression. Lower compression ratio is desirable because higher compression ratio may result in an increase in the work input to the compressor and decrease in the volumetric efficiency. We can understand by this one. We know that for an isentropic process, T2 by T1, or for a polytropic process, T2 by T1 can be given as P2 by P1 to the power n minus 1 by n, where n is your polytropic index. If P2 by P1 is higher, then compressor discharge temperature CDT T2 will also be higher, because for a given input temperature, that is your T1, which might result in the lesser compressor life as well. Also, we know that volumetric efficiency of a compressor is given as 1 plus C minus C P2 by P1 to the power n by 1 by n. If P2 by P1 is higher, that is the ratio of compressor, the compression ratio. If P2 by P1 is higher, this whole term will be higher. So this whole term will, if this whole term has a higher value, this is with the negative sign, and it will result in the lower value of volumetric efficiency. So it is expected to have a lower value of compression ratio. Among different refrigerants, ammonia has compressors are generally water cooled because of the higher compressor discharge temperature. R11, R12 refrigerant, if these are used as a refrigerant, the compressor are generally air cooled. It means compressor discharge temperature are not very much higher, so we can cool it by air as well. Where the ammonia refrigerant is used, so compressors are generally water cooled because it has higher CP value. Next one is your specific volume. The specific volume of the refrigerant vapor at the evaporator temperature indicates the theoretical displacement of compressor. Reciprocating compressors have low specific volume and higher pressure. Centrifugal or turbo compressors have higher specific volume and lower pressure, and the rotary compressors have intermediate pressure and volume of suction vapor. So these were the different thermodynamic properties that are used. Now we will discuss about the few physical properties. Initially we will discuss about the chemical properties. So chemical properties are toxicity. The refrigerant should be non-toxic. For example, NH3 is toxic in nature, so it cannot generally be used in our domestic purpose application. Flammability, it should be non-flammable in nature. NH3 is toxic as well as it is flammable in nature. Action with the oil. The refrigerants such as R11, R12, which are fully miscible with oil, which completely mixes with oil, and the refrigerant which are completely immiscible with oil, which do not mixes with oil, do not create any problem in the refrigeration system. But the refrigerants like R22, which are partially miscible with oil. Initially we discussed about the refrigerant which completely mixes and the refrigerant which do not mixes with the oil, do not create any kind of problem in the refrigeration system. But the refrigerant like R22, these are partially mixes with miscible with oil, create problems in flow, and choking problem occurs. It means the blockage of the pipe. To avoid such situations, synthetic oil is used in place of mineral oil. So to avoid these situations, we use generally synthetic oil in place of the natural oils. There are few points to be noted. Oil separators is installed between compressor and condenser. If a refrigerant do not completely mixes with oil, or it is partially mixes with oil, so there are some arrangements which we need to use. Oil separators are installed between compressor and condenser. Oil separator is not required to be installed if refrigerant and oil are immiscible at condenser temperature and pressure. Sensing bulb is placed at the exit of the evaporator. So these are few arrangements we can make if the refrigerant are mixes up with the oil or it does not mix up with the oil. Action with the another property is action with the material of construction. There are few examples. If ammonia is the refrigerant and if the material of construction is your copper, so it attacks the copper. So what are the favorable material which can be preferred? These are wrought iron. Ammonia, if ammonia refrigerant is used, the material of construction may be of wrought iron. If freon or halocarbons are used, it attacks the aluminum material. So the favorable material which can be used is your copper. Now we'll go with the physical properties. The physical properties are mainly cost. It should be low. As we all need that any refrigeration system should be economical, and any refrigerant that is being used, it should be low cost. Otherwise it will be very difficult to use it at every location or every application. Viscosity should be low for the ease of flow of the refrigerant. Leakage detection. Any refrigerant should be detected by the leak if it leaks. So leakage detection should be done. First, there should not be any leakage from the refrigerator. If it leaks, then its detection should be as fast as possible by simplest method adopted. There are few methods, that is halide torch method, soap bubble method. These are generally the ammonia swab test. These are generally the tests which are conducted for the leakage detection of the refrigerant. Halide torch test is done for in the presence of a freon. The color of light will change from blue to bluish green. If freon refrigerant is used and if it is leaked, then the light of the color will change from blue to the bluish green. Soap bubble method. If ammonia leaks, it is detected by the sulfur stick method. If ammonia is leaked, it is detected by the sulfur stick method. In the presence of ammonia, white fumes of ammonium sulfide are formed. If sulfur dioxide leaks, it can be detected by the ammonia swab test. So these are different tests which are conducted for the detection of refrigerants, leakage detection of the refrigerants.